Greetings. I welcome you all to the new lecture for this course. Uh, till now we have had multiple rounds of discussions on the metallurgical wastes, and now we will be focusing on the electronic wastes, which will be the next segment of this course. And first we will be focusing on the recycling of the waste printed circuit boards, and then gradually we will be moving towards the recycling of batteries. So the couple of lectures that will follow presently will be on printed circuit board recycling, whereas afterwards we will be focusing on the batteries. Now when we think of electronic waste recycling, the first thing that we have actually done the categorization. So coming back to what we had studied previously, we know that electronic waste basically means the waste that is coming back from the consumer end. So suppose that there is an industry that produces electronic devices, electronic gadgets. So these gadgets will be coming into the market, and people will buy these gadgets, they will use it. The gadget performs its application for a given, let's say, span of its life, let's say 5 years or 10 years or whatever it is, and then after its intended use, it reaches its end of life. So there could be some technical faults in the electronic device, or it can experience some sort of mechanical damage. Due to also whatsoever reasons, the device may stop functioning. What happens when these devices are out of their use? Most of these devices will be gradually discarded by the users. Now these discarded electronic devices are basically ending up in the material scrapyard. So if we look at the general scrapyard, we can see discarded automobiles, we have discarded cars, we have a segment that has the discarded electronic wastes as well. So when we look at e-waste, the first thing that really comes to mind is we have those wastes that are stacked in the scrapyard. So what do we do with such a stack of electronic waste? Now one way is to clearly identify the valuable materials in it, just as we have done with the metallurgical wastes for, let's say, aluminum, copper, zinc, and then we design the recycling strategy and then extract the valuable materials. But we have a slight bit of a challenge here. The challenge in electronic waste recycling is we have no control over what we are trying to recycle, because when we look at e-waste stream, it can contain large segments of variety of electronic devices that can be discarded. Now the first step is what we have discussed so far and emphasized so many times: sorting of wastes. So if we sort our electronic wastes into various categories, the broad categories of e-waste we have already discussed. So there could be small equipments, large equipments, and so on and so forth. So if we sort our wastes right at the beginning of recycling, the moment we, let's say, get a stream of e-waste, what do? We should sort it, because it helps us in developing the recycling strategies for these sorted waste materials. Now in the present lecture course, we are focusing on two main streams, the PCBs and the batteries. But of course there are so many different types of wastes that we can actually explore and have lengthy discussions and detailed recycling strategies. Of course such investigations really help us to identify what are the valuables that we can extract directly, or what are the valuable materials that we can produce using these raw materials. So we will now be having some general discussions on e-waste recycling, and then we will gradually focus on waste printed circuit board recycling. Let's go. So we have e-waste recycling. We know that the recycling of e-waste is one of the most challenging aspects of modern day recycling. So e-waste recycling is one of the segments of wastes generated by modern society. And there is the problem of material cycle. So what do we mean by material cycle? We already know. So we have the generation, application, and then it's recycling. But we need to understand material cycle in e-waste. So material cycle of e-waste has to be discussed. And we have already seen that we have the categorization of e-wastes. So coming back to those categories, the categories are small equipment, large equipment, telecommunication devices, signals and telecommunication devices, temperature regulation, so ACs and temperature regulations, ACs and refrigerators are here, lamps and lights, and of course we have screens. Some other categorization can also be done, but we know that these are the primary categories. So when we think of these categories, what is the first thing that we should be thinking of? Sorting of e-waste. So whatever is the stream, we sort it on these into these categories, and then we devise our recycling strategy. So, and we know that the challenge that we basically talk of is that the complex nature of the discarded materials. Complex nature of discarded materials. So this itself means that we have wide variety of materials. We have metals, composites, some parts of ceramics also, and so on and so forth, which are directly used in, and of course we have polymers also. So these materials are directly used in e-waste, electronic devices, which end up in e-waste. So think of it in this direction. What are the materials that we are using to make the electronic devices? Those materials are going to show up when we are looking at the electronic wastes. Of course, unless until the equipment itself does not experience heavy wear and tear, we don't expect the material to totally disappear. Say for instance, all the metal components of an electronic waste is lost. This may be due to certain actions that can happen, but generally speaking, whatever materials that we are adding while manufacturing, will end up in the e-waste. And then this heterogeneity of materials itself, this creates the complexity. So when we talk about complexity, it is just these materials creating the catch, that we have to deal with metals separately, we have to deal with polymers, we have to deal with composites, and if at all there are other categories also, we have to deal with these materials separately if we wish to extract valuable materials from all segments. Of course, there is a possibility of discarding some materials and using the others, while that may be economical, but if we are strictly speaking about utilizing every aspect, then we'll have to segregate these wastes. And these categorization of materials within e-waste is different for every category. So small equipments may have different composition, large equipment may have different composition. Similarly, telecommunication, screens, lamps, temperature regulating devices, every device has its own composition variation, and handling this becomes a challenge. Plus, there is one more inherent challenge that we should be noting. Electronic devices can be manufactured by large number of companies. Every company has its own way of making their own devices. So cell phones can be prepared by large number of companies. Discarded cell phones, when it reaches the scrapyard, when it reaches the recycling unit, it may be originating from a different company altogether, for which the recycling industry may not be completely ready. So one has to adopt a new strategy, how to accommodate as much e-waste of a given waste stream as they can. We'll continue. The proportion of inherent chemistry of materials. So we are basically talking about proportion of inherent materials. We don't know. It has to be analyzed. Varies a lot of each chemistry of materials of each waste stream. And again, I'm thinking about, this is basically a sorted waste stream. So this proportion is a big variable actually. The proportion of inherent chemistry of materials of each waste stream needs to be analyzed. And one has to think about developing some sort of overall data bank before we even start developing our recycling strategy. Why is this necessary? I have just mentioned, say suppose we are thinking of recycling TV screens or let's say washing machines. We'll be discussing those types of wastes also. So we know that TV can be produced by large number of manufacturers, and the components that are used to make these electronic devices, they vary in composition, they vary in chemical composition, and their proportion in use that is used to make these devices can vary from company to company. So that data bank is extremely important to get. This data bank can help us in understanding how we should proceed in a ways that can accommodate to most of the wastes. Let's say if we are looking at TV recycling, most of the TVs that end up in recycling unit can be recycled. So proportion of inherent chemistry of materials, inherent chemistry of materials. So what materials are we talking about? These materials. Of each waste stream. So which waste stream? Again, we need to be very focused and we've already mentioned that it is basically a sorted waste stream. So when we think of waste stream, these waste streams, and we have to be at times very specific, let's say example TVs or refrigerators or ACs, etc. So when we think of sorted waste stream, it better be classified even before it reaches for recycling, and that needs to be analyzed so that we get a good overall output. Now, why exactly is this important? We'll look at some of the classic waste streams that we can really identify. So household, a general household can have, let's say, washing machine, or at times we are more comfortable with, let's say, ACs or refrigerators or televisions. So we look at these waste streams first, because if we understand the recycling of these equipments, we will be able to understand the recycling of WPCB, and why exactly WPCB is one of the most important raw materials when we think of e-waste. So we will go there, but before that we are now looking at these examples. So material composition of e-waste. Consumer end, we have this consumer end, and we have the generation of e-waste. And we are again assuming that we have sorted the waste stream, and then we have to basically analyze chemical composition of the wastes. Now we will be taking the example of washing machine so that we understand the recycling route better. Now, so we have discarded end of life washing machines. So EOL is basically end of life, WM is washing machine. So we have discarded washing machine, and then we have, how do we basically recycle? So this is basically a recycling strategy or recycling route for EOL WM, end of life washing machine. So we have manual dismantling, which basically means the removal of parts. For reuse, direct reuse, we just take the discarded washing machine and then we just start dismantling the machine. Of course, this is done manually. Why should we? Now one just might wonder, is it really safe to handle electronic wastes manually? So, and is it really worth it? So one just might want to argue, let us just put everything into a shredder and let us just get some shredded scrap. It may work, but at times we need to understand that manual dismantling can help us get those wastes recovered right at the front that may hinder the process in the other processes that follow, or we may not recover them at all, and because they are shredded, they may just dilute the concentration of materials that we may get in case of sorted and manually dismantled materials. So it is just important to recover materials as we can. Manual dismantling can help us get those materials separated out, so that main shredding and recovery just gives us good overall material output. And when we are thinking about shredding, mostly we'll get metals and plastic wastes. So those separation can be done properly and nothing else interferes. That is why we are focusing on manual dismantling. And of course, this is just one of those strategies. There are many strategies that may totally avoid manual dismantling. They have a different way of removing those components that can interfere. But of course, we are just looking at one of those strategies wherein we have manual dismantling. And then we can just send these parts for reuse. What else we have? Shredding. And this leads, and after that we can just go for magnetic separation. We have eddy current separation, and then we have residual solid, plastics. Now, discarded end of life washing machine goes into manual dismantling, wherein we get our parts removed for reuse. Then we have shredding, and then we have magnetic separation followed by eddy current separation. But what really happens in shredding? So we have the reduction of size, and then the shreds are formed, and these shreds reach magnetic separation where you get ferrous scraps. Eddy currents are going to give us non-ferrous scraps, and we know that using magnetic separation and eddy current separation, we are going to get ferrous and non-ferrous scraps. So metal parts are totally removed just by thinking and arranging the processes in a very befitting manner. So we shredded, we added magnetic separation, removed the iron or ferrous scraps, then we add eddy current separation, we remove the non-ferrous scrap, and then whatever is left, we have some parts of residual solids and plastic wastes. So most of the wastes are already taken care of, but one has to think what is the best route for their own, let's say, recycling unit or industry. Now, when we think of manual dismantling, what are we talking about when we are thinking of manual dismantling? Manual dismantling means we will be having salt waste. So if we have an front loading automatic washing machine, we can have these types of wastes also. So salt waste is one of the waste that is generated. Of course, this is in very less quantities, but it is there. So salt waste. We have power cord we have condensers, hose, PCBs. Again, the PCB is here. So we PCB is present in a washing machine. That PCB is altogether different from PCB that is present in a computer, for instance, or a cell phone. So PCB is there in the electronic device, and we need to remove it before we just put it into a shredder, because it is going to somehow interfere in the overall material recovery. And once we have done the shredding, we can't really get a good recovery from the PCB component itself. We might get some metal out of it, but it is going to get affected, or the overall metal recovery may be affected because of indiscriminate addition of PCB into a shredder. Of course, directly with the overall body of the washing machine. And of course, there is the motor. So we have so many components that are present: salt, condensers, hose, PCBs, and the motor. And this can be done by manual dismantling. So this is the reason why the dismantling becomes a important task before we send our scrap to shredding. Now we'll look at the material balance, because this is also important. We have just seen a overall process, and of course about manual dismantling also, but we do not know much about what is the material balance. So we'll discuss material balance. Total waste, material from manual scrap, dismantling, and separation. So one part of waste is coming from this end, manual dismantling. The others will come from the magnetic separation and all. Plus total waste material from shredding. And other operations that follow, that means magnetic separation or eddy current separation. So shredding till magnetic separation and beyond, we have the other fraction. And of course there is the wastes, other wastes. So some waste we really cannot categorize, so those wastes are also to be taken into account. We see that 24.99% is from manual dismantling, 74.71% is by shredding, and the rest is waste. And when we think about what we could recover from scraps, so we can just have a glance that plastics and metals have an internal division within this fraction. So plastics could be having 37.3%, whereas metals could be 37.41. That gives us the overall. Which means we have seen the division of metals within this as an example. We see that just by looking at washing machine, we see this split. Now, such discussion can be done for other components as well. We'll look at one more example of ACs, air conditioners, and then we will be then focusing into the WPCB. So let us just draw the same diagram, material balance and all that. We have the discarded EOL AC, which gives us manual dismantling and separation. Then we have the shredder. Then we have magnetic separation. Then we have eddy current separation. And finally we have residual solid and plastics. So we know what just previously we had seen what are the inputs and outputs. We'll just discuss what are the components that we see in manual dismantling. So if we look at manual dismantling, what we can get is basically the CFCs. CFC, power cords, copper pipes, condensers, PCBs again, PCBs always there, almost always there. We can have compressor or motors. So we have CFC oils. So in whatever form the CFC is present, it is there. And we also see what is the material balance. So we'll look at that. The material balances. Again, we'll do the same in whichever unit we are trying to explain. So in most of the cases, of course, it is in mass. So total waste material in manual dismantling stage plus total waste material in shredding and other operations. Plus waste. So we know that in this case we are going to get nearly 58.6%. In this case we are going to get 40.2%, and we have waste of 1.2%. Something that we could not accommodate here. Now again, the division in plastics. Plastics can be 14% nearly, and metals could be 26.1. So that is the division here. So it could be nearly 14 and 26% is the division here for the shredding component of the waste. Now we see that there are so many different types of materials that we can recover from a washing machine or an AC, and it is very important to tap those materials before even we send it to the shredder. Now, we will be continuing this recycling of e-waste in the upcoming classes, wherein we will now be focusing on why we really need to go into specific wastes like WPCBs. We will continue next class. Thank you.